All right, welcome to Year 11 Maths Methods, Home Edition. Okay, so today we are looking at exercise 6C, which is looking at factorisation of polynomials. If you're following along in your textbook, this is page number 220. So last lesson, or when I say last lesson, the last time we had maths, we also looked at doing long division of polynomials, and it was quite a process. Yep. And one of the things I did articulate is you need to just practice it over and over, making sure that you are lining things up and setting things out correctly. Where people were making mistakes was where the process wasn't followed correctly, writing was messy, and errors are made when things aren't lining up. So let's consider the question here where you got p of x. If you were to divide that by x take away 2, you could do long division, and ultimately down the bottom here it will tell you if there is a remainder. If this comes out to a 0, there is no remainder. If it comes out to a number, obviously that is the remainder. So by doing this division here, we can see that the remainder is 25. Cool. That can take some time to do that. The good news is we have a shortcut way, which is the remainder theorem, which can make things a lot quicker when we are doing that. So essentially what the remainder theorem is, when we have a coefficient of 1 in front of the x as a linear factor, the remainder theorem says we're just substituting in the negative of this value here, and they denote it by alpha, the Greek letter alpha. Substituting in the negative of this, so the negative of negative 2 is positive 2. What we do, we substitute positive 2 into the function and we evaluate what it comes out to being. Let's actually do that process now. So as I said, the reason I chose positive 2 is because it's the negative of that value there. So substituting in positive 2 into the function, so wherever the x is, we're putting 2, evaluating it. Oh, surprise, it comes out to being 25. Cool, that tells us that the remainder when x take away 2 is divided into this cubic is 25. Now that's a lot quicker to substitute 2 into this expression, and you can quickly evaluate that rather than doing the long division. Cool. So that is the remainder theorem. It goes on a little bit more in more detail. Not all the time are you going to have a coefficient of 1 in front of the x. So there's going to likely be another number in front of x. In that particular case, the notation this textbook uses, they denote the coefficient in front of the x as the Greek letter beta, and obviously this value here as the Greek letter alpha. So if there is a number that's not 1 that's in front of the x term here, the value that you're going to substitute in as part of the remainder theorem is the negative value of this here, so the negative value of alpha divided by this beta value here. We'll have a look at an example with that. Now, the reason when it's just a 1 in front of the x term here, so a 1 as the coefficient of x, obviously it's just going to be the negative of this value, so negative of the alpha value, divided by 1 is just the negative of that alpha value, which we're speaking about. So it's a lot easier if it's just one lot of x something over here. But if there's another number here, a 2 or a 3, etc., you just need to divide that by that number that's in here. Alright, let's have a look at some examples now with this. This is example number 9, which is located on page 221 of your textbooks. Cool, so we've got the function p of x. Cool, we've got that there, and it's saying, hey, what is the remainder when it's divided by x take away 2? Now traditionally, in the old days, like last lesson, you would have to do the long division, work it all out, and eventually down the bottom you'd find out what the remainder is. Good news is I've just shown you what the remainder theorem is, and it's going to be a lot quicker to find out what that remainder is. So using the remainder theorem, it says we're going to substitute in the negative of this alpha value here. So the negative of -2 is +2. So what we're going to do is we're going to find out what p of 2, so substituting +2 into this function. So wherever we see the x, we're going to substitute in 2, which they've done. We're evaluating that, obviously finding 2 cubed, doing -3 multiplied by 2 cubed, etc., etc. We find out that it simplifies down to being 6. That tells us that when you divide x take away 2 into this, the remainder is 6. It is a lot quicker, hopefully, as you can see, to use the remainder theorem rather than doing long division. Let's have a look at the next example. In this case, it's saying use the remainder theorem to find out what the remainder is when 2x plus 1 is divided into this function. In this case, obviously, it's not one lot of x here. There is a beta value that we do need to consider. Obviously, the beta value here is 2. So, to work out what we're going to substitute in to p of x as part of the remainder theorem, remember it's going to be the negative of this value, so negative of the alpha value, so in this case +1, the negative of that is going to be -1, divided by this beta value, so divided by 2. So let's substitute in -1 divided by 2 into the expression, or the function p of x, sorry. So wherever we see x, we're going to substitute in -1/2. Yeah, there's some fractions there, but as year 11 students in methods, you guys should be able to handle this. Evaluating it and simplifying down here, we get 39/8. So the remainder is 39/8 in this particular case. Again, hopefully, even with fractions, it's still going to be a lot quicker than doing long division. Now, there is a note here saying, yeah, you could do long division, but now that we've got the remainder theorem, it's not necessary to perform the polynomial division to find the remainder. So as soon as you hear a question that's just asking, hey, what is the remainder? You don't need to go through the whole process. You can just use the remainder theorem there with that one. You think I'm sort of harping on about it, but there are students that do not read the question carefully. They will go, okay, it's asking me to find out what the remainder is, and they will still do the long division process, which will work, but it's going to take you a lot of time when you don't necessarily need to do that. Okay, now looking at worked example number 10. Oh, this can work the other way as well a little bit. So here they've given us p of x, and there's an unknown value a here. They're saying when x take away 2 is divided into this, the remainder is 4. So in this particular case, they've given us what the remainder actually is. We just need to use and apply the remainder theorem to find out what this unknown value is. So we know that to use the remainder theorem, if we were to divide by x take away 2, we need to do the negative of that as part of the remainder theorem. So the negative of -2 is obviously +2. It would be +2 that you're dividing into this. Oh, sorry, let me dial it back. It's +2 that you're going to be substituting in to this expression. So you'll be doing p of +2 into this expression. And when you substitute in +2 in each of these spots, it should equal 4. So actually doing that, where we see x, we're substituting in 2. So 2 cubed is 8, 2 times 2 is 4. We have the plus a, and that will equal 4. Okay. Once you've got that happening, it's a matter of rearranging things to find out what that unknown value is. In this case, we're moving 12 to the other side. A is going to therefore be -8. Cool. Oh, now, just when you thought it couldn't get any more exciting, it does. We're now going to look at the factor theorem. Now, if we dial it back and we think about what factors are things that when you are dividing them in, there's no remainders. It fits in perfectly. So the remainder is 0. The good news is we can build upon the remainder theorem to bring us to the factor theorem that basically says if you have a linear factor, when you do the remainder theorem, essentially. It's the same as the remainder theorem. If it comes out as being equal to 0, it therefore would be a factor because it fits in evenly. So essentially that's what this is all saying about the factor theorem. Yeah, so if you, as I've alluded to. Let's have a look at it in an example. So it says here, worked example 11, it says show that x plus 1 is a factor of this expression here, but then it's also going on and asking us to find out some other linear factors as well. So as we've just been talking about, if we were to use the remainder theorem and hence also the factor theorem, if we were to put in or use the remainder theorem, which was to substitute in the negative of this alpha value, so the -1, if we were to substitute in -1 into this expression here, so doing p of -1, as this is a factor here, when we substitute in -1 into this expression, it should come out to being equal to 0, which says it is a factor. So substituting in -1 into where x is here, evaluating it, surprisingly, it comes out to being equal to 0. So this does mean that x plus 1 is a factor, because when we substituted in -1, using the factor theorem, it came out to being equal to 0. Cool. Now once you know one of the factors, which they already told you here, it was a factor, you can go ahead and do long division to find out the other factors. So what happens here is we're going to do x plus 1, we're going to actually do the division of it here. Long division comes out and we end up with x squared take away 5x plus 6 as the quadratic. Once you have the quadratic, you can factorize the quadratic and that will break it into the other factors. So in this particular case, when you've got x squared take away 5x plus 6, that factorizes to x take away 3 and x take away 2. So those two are the other linear factors. Cool. Worked example number 12. Oh, cool. So they're making you factorize this particular expression completely. Now before you can factorize this here, you need to figure out what one of the linear factors is. So this is a little bit of trial and error. Yep. So what we're going to do is we're going to use the factor theorem and we're going to pick some numbers that we're going to substitute in here to try and discover which one of those evaluates to 0. When we get it right and it equals 0, we know that what one of the factors is. So you're probably sitting there going, okay, well, what numbers am I going to choose, or what numbers am I going to guess will possibly lead to being a factor? What you need to do is consider this on the end here. So in this particular case, we've got positive 6. I would be starting off by trying each of the numbers that is a factor of 6. So things that fit into 6 are both positive and -1 fit into 6, both positive and -2 fits into 6, both positive and -3 also fits into 6, and both positive and -6 also fit into 6. So these are the numbers I would be trying first. Now again, with these numbers that I'm going to be trying in, as mathematicians, I don't like to say we're lazy, but we are a little bit lazy. So I would be starting with the numbers that are easier to substitute in. So I'd be trying positive and -1 first before I try positive and -6, because 6 is a big hard number to substitute in here. I'm kind of joking there, you could do it. But let's start off with positive or -1. What I'm going to do is I'm going to start with positive 1. It's even easier to substitute in than -1. So substituting in positive 1 into this function here. Cool, so 1 cubed take away 2 times 1 squared, etc, etc. We get these values. When you add them together, it comes out to being equal to 0. Oh wow, that's awesome. The very first number we tried came out to being equal to 0. Again, this is good news. This tells us that we can discover what one of the factors is. So because we substituted in positive 1 and it came out to being equal to 0, remember the remainder theorem and the factor theorem, it's the negative of this value that tells us the factor. So in this particular case, the factor is actually negative, or x take away 1 is the factor. Don't get tricked into just going, okay, well 1 fitted in, oh, the factor's x plus 1. No, it's the negative of that value. Okay, so 1 fitted in here, the factor is x take away 1. Okay, now the good news is once you have one of those factors, you can then go ahead and do the process of long division to find out what those other factors are. So here we've gone through, we've got the quadratic. Once you have the quadratic, you can factorize this quadratic, x squared take away x take away 6. It factorizes to x take away 3, x plus 2. So these are the other two linear factors. Now, some of you might be thinking, okay, is there any other way of doing this? Well, let's consider if we had have tried some of these other values. If you had have tried negative 1 substituting it into here, it doesn't come out to being equal to 0, so that's not a factor. So x plus 1 is not a factor. But if you had have tried x positive 3 in here, so p of 3, when you evaluated it, it would have come out to being equal to 0. In this particular case, when you substitute in p of 3 and it comes out to being equal to 0, it tells you, or means that x take away 3 is going to be the factor. Likewise, if you had have tried while you're trialing an error, you might have substituted in negative 2. P of negative 2, it would have came out to being equal to 0 as well. That should have said to us, okay, it's the negative of negative 2, which means x plus 2 would have been another one of those factors there. So sometimes you could have, rather than doing all this long division process, just trialed and errored these numbers and you could have got those there. But if you definitely want to make sure that you know what these factors are, once you find one of them, you can do the long division to find out those other ones there. Yeah, sometimes the number on the end is not a nice number like 6. It could be like 24, where there are lots of factors that you'd have to try. Cool. Now, again, this can be done on your calculator. If you wanted to do it on your calculator here, go to interactive transformation and factor. That will pull up the factor function, type in the expression, which we were just looking at, close the brackets, execute that command, and it will spit out the factors, which is good. One last thing I want to talk about in this video is what's called the rational root theorem. So again, you might have a scenario like this one here. You've got 2x cubed take away x squared take away x take away 3. Now, as I was saying before, okay, well, here's the number on the end, it's negative 3. Why don't we just try all the different values that fit into negative 3, so each of the factors is negative 3. If you did that, so you tried 1 and negative 1 and positive 3 and negative 3, you'll quickly discover that none of them come out to being equal to 0. So that tells you straight away that it's not going to be an integer solution, so a whole number solution there. So then we need to ask ourselves, does it have a rational solution? Which means, is it going to be a fraction that's going to come out for this solution? So in this particular case, we need to use what's called the rational root theorem. And basically, again, we're going to be using and looking at these alpha and beta values. What we're going to be considering is that the beta value is going to be the number or the coefficient in front of this leading term. So in this particular case, the beta value is going to be 2. And the alpha value, we need to try each of the factors of this number on the end, the constant. So as we said before, all of the factors of that are positive and negative 1 and also positive and negative 3. So essentially what we're going to be doing is checking, substituting in, as we said, the beta value is going to be on the bottom. In this case, it's going to be 2, but we're going to be trying on the top the alpha value as being either positive or negative 1. So we're going to have to try positive a half and negative a half and see if that comes out to being equal to 0 when we substitute it in. And we also need to try both positive 3 over 2 and negative 3 over 2. So trying each of those, eventually you'll find out that if you substitute in 3 over 2, so into it, it comes out to being 0. In that particular case, it tells us that we have found the factor. So the beta value is this one on the bottom, which is obviously 2, and the alpha value is the negative, this one on top, so it's going to be negative 3 here. That can be a little bit challenging, but I believe that you guys will be able to have success with that. Have a look at worked example number 13. Again, here you could try values here that are factors of negative 5. Pretty quickly, after you've tried negative 1 and positive 1, you'll find out they don't equal 0. Likewise with positive and negative 5, they don't equal 0. So then you have to go and consider the rational root theorem. So again, in this particular case, I'd be looking at the beta value being this 3 here, and then trying the other the alpha value as the factors of negative 5, so both looking at positive and negative 1 and positive and negative 5. Eventually you should find out that it's negative 5 over 3 that does evaluate to being equal to 0, which says that the factor that fits in is this beta value, which is 3, so 3x, that's the negative value of negative 5, so plus 5 is the factor. Again, you could go ahead and do division here to go ahead and find out obviously what the other factors are here. They're suggesting using completing the square to do that. Thank you very much for listening up. Please have a go at this exercise today.